So it's a great pleasure to introduce a great mathematician, physicist, and a friend of mine for 20 years, Anton Kapustin.
Thank you. So I'd like immediately to, make a disclaimer. I'm not a mathematician. So, please don't, put unreasonable demands on me. Instead, I'm gonna, also another disclaimer is that, okay, the title of the workshop is wall crossing, quantum integrable systems, and TQFT. There'll be nothing about wall crossing. There'll be nothing about integrable systems.
So then the next statement should be, I'm not a friend of his.
Okay, no, we're friends, so we're still friends.
Thank you.
But it will be talk about TQFT, so I guess it still works. So I didn't give Ludmil the title, so I'll give it now. So. And this is a general subject, anomalies in topological quantum field theory. So I apologize to those who've listened to some version of this talk before, but I'm sure many people also didn't. So don't worry about overlap. I'll try to, I'll try to make a more general introduction to the subject and cover some recent advances. So that's a very old subject, and anomalies have been discovered, I think, anomalies were discovered in the 60s. Actually, they were first discovered in the 50s, but the guy who discovered them, what's the anomaly he discovered? Well, he was checking that certain symmetry of the classical theory survives upon quantization, and he couldn't show that, and he was so frustrated that he quit high-energy physics and switched to something else. So that wasn't the discovery yet because he didn't publish anything. But in the 60s, it was rediscovered, and the people nailed down the problem. The so-called ABJ anomaly. This is Adler, Bell, Jakiv anomaly was properly described. And there are actually several kinds of anomalies, but this is the oldest one. So classical symmetry does not survive quantization. So the second kind of anomaly, which have been closely related, is so here symmetry is a global symmetry, meaning that global symmetry. What does it mean? Well, the physical terminology is the global symmetry is a symmetry where the parameter of the symmetry transformation is just a constant. It's an element of some group, of some finite group. Oh, sorry, not finite. Element of some finite dimensional Lie group. So in that, that's what means global symmetry, as opposed to gauge symmetry, where the parameter is an element of some function on a manifold with values in the group. So the ABJ anomaly has to do with situation when some global symmetry doesn't survive quantization. Now, you can also ask what happens if the symmetry which doesn't survive quantization is a gauge symmetry. Now, gauge symmetry has a rather different physical status. So it's not a physical symmetry because actually all observables are invariant under it, and it's going to be redundant in the description. And the constant is, while ABJ anomaly is interesting, but doesn't mean the theory is bad. If the anomaly affects the gauge symmetry, it means the theory is inconsistent. So gauge, these are called gauge anomalies. So here gauge symmetry does not survive quantization. And the third kind of symmetry, the third kind of anomaly is called the 't Hooft anomaly. So it arises in the following situation. Suppose you do have a global symmetry which doesn't have any ABJ anomaly. But then you can try to gauge it. What does it mean? Well, I have a parameter of the symmetry, which is, you can think of as a function. Well, a parameter of a symmetry is just a constant, so some element of the group. But you can imagine that instead of thinking of it as an element of the group, you can just think of it as a closed zero cochain with values in the group. And then if you relax the condition that it's closed, you get some zero cochain in values in the group, and that's gauging. Now, well, if you of course the original theory may not be invariant under these larger symmetries, but you can try to modify somehow the action. And first of all, the first thing you do when you gauge a symmetry, you also introduce the gauge field, that is, which is some there's some one cochain with values in the group. But it may not work. You may, so that is, your theory now has an extra field, this one cochain. You can try to modify. Well, you can try to invent some more general action, which reduces to the original one when you set this one cochain to 0. But you may not succeed. So if there may not be any extension of this global symmetry to a gauge symmetry. In this case, one is an anomaly, a 't Hooft anomaly. So anomaly is an obstruction to gauging a global symmetry.
Anomalies appears for determinants, essentially.
Not necessarily. That's what actually the main point of my talk is that. Yeah. So okay. So next we need to understand how to. Well, I am focused on the third kind of anomaly because actually, typically, say the first kind of anomaly. Well, they're all closely related, but say the APJ anomaly often arises from that 't Hooft anomaly, like in situation when you have a global symmetry group, which is a product of two groups, and then there's some sort of each of these subgroups by itself doesn't have a 't Hooft anomaly, so you can gauge it, but there's sort of a mixed anomaly, which says that if you gauge one, you cannot gauge the other. So if you decided to gauge one subgroup, then the other factor becomes afflicted with the ABJ anomaly, so you cannot gauge two. So that's a typical example. So I'll just focus on the 't Hooft anomaly from now on. Now and then, of course, this subject has been studied to death since the 1970s, but there are other special, well, in the case which is important for physics, but not the most general. So, special case G, so our global symmetry group. Is a compact, connected, well, reductively group. Yeah, okay. I first wanted to say semi-simple, but then yeah.
Arbitrary field, but if you want.
Well, I wanted to. Yeah, at some point I changed my mind about what I want to say. I want to say semi-simple. Wait a second. What about U1? Okay, so
it's compact group. I mean.
Sorry?
You mean compact group, or make your mind because
yeah.
C2R is also reductive.
No, it should be compact.
Okay, just compact.
Well, it's not actually not terribly important. The important conditions here is it's connected. So. Compact. Okay. Okay. No, it's not redundant.
Any compact group is an classification. It's a compact form of.
Okay, fine. Yeah. Okay. So anyway, so why connected is important? Well, I'll talk about it later, but let me just say what the answer is in this case. So in this case, the anomalies arise essentially from only one source, from fermions, and moreover, all anomalies in this case can be sort of realized by free fermions. And this is a very simple theory because the partition function can be evaluated, as some determinant of Pfaffian of some Dirac operator, and then you can study its invariance under symmetry or under gauge symmetry, because you need to commute the 't Hooft anomaly, you need to figure out whether it's gauge invariant or not. And the answer is very simple, is that, well, let me formulate it this way. That anomaly, this non-invariance of the theory under gauge symmetry, is always some phase of the partition function, and you can sort of cancel it at the expense of placing your theory of free fermions at the boundary. So, well, we imagine some d-dimensional space, some space-time MD, and then imagine that it's on the boundary of d plus 1 dimensional space-time MD plus 1. And then you can always cancel the anomaly by imagining that in this d plus 1 dimensional space you have some topological field theory. Well, the theory on the boundary is not topological, but in the bulk you have a topological field theory, which is actually topological gauge theory, which depends on some gauge field for this symmetry. And this topological field theory has an action which is gauge invariant if the manifold N doesn't have a boundary. But if the manifold N does have a boundary, then it's not gauge invariant. And this boundary term in the variation of the action precisely cancels the anomaly of this boundary theory. So that's how it works. That's the most general case in the case of free fermions. And actually, and conversely, if you just assume that this group is like that we can classify all possible anomalies, and it turns out that they're always of this form. So, okay, so this mechanism sort of canceling anomaly called anomaly inflow. So we have something gauge invariant without boundary, but then we have a boundary. There's an inflow sort of anomaly which is cancelled by whatever lives on the boundary.
Plus one is classical action.
Well, you can imagine that, well, when a gauge, we had two options. When a gauge, you add a new field to the theory, gauge field for this symmetry. And you can imagine that it's just fixed background gauge field. You don't integrate over it. It's just a classical background. And you just study the invariance of the partition function of this boundary theory under the change of trivialization of the bundle. And then it's a classical. And then similarly here, you have a fixed gauge field, which is classical gauge field. But you can also imagine integrating over it. That doesn't really matter.
It can be all possible summation over all possible.
No, you don't need to sum, just particular. It doesn't really matter because this field theory defines an arbitrary manifold. You can just pick, imagine this guy just one component of a boundary of this high-dimensional manifold. So now we can even write down explicit formula for this topological field theory, well, for the action of this topological field theory. And the action of this d plus 1 dimensions is the Chern-Simons action. So, well, first of all, such actions actually exist only when d plus 1 is odd, and therefore d is even. So, just give an example. Say, suppose the group is U1, and d is 2m, and then you write the action, Chern-Simons action.
One can write also, if it's n d plus 1 is close, you can usually write this integral of curvature of d plus 2 dimension.
Yeah, but here we're interested in the case when n does have a boundary. So we don't want to introduce a d plus 2 dimensional manifold. But indeed, this formula is a bit schematic because A is a connection. So A is a connection on some principal U1 bundle over n. And so it's not a form. So, well, dA is a well-defined 2 form, but A is not a globally defined 1 form. So when some gymnastic is needed to interpret this, and one way is to introduce into d plus 2 dimensional manifold. In case when n doesn't have a boundary, you can introduce a d plus 2 dimensional manifold whose boundary is n, although of course you can ask, okay, what about if it's not actually a boundary of anything, because it could be not cobordant to 0, then you have a trouble.
What is
Some principal, well, what is the gauge?
over what?
Over n.
Just general, no topological restriction. You can add some additional
Like what?
over topology.
Just to connect It's a gauge theory, so just integrate over, well, if it's a quantum one, integrate over all U1 gauge fields. That is all bundles. Also some over all topological classes of bundles. But anyway, we're not doing that. We're just saying, suppose, this is essentially a classical problem so far. A is just some fixed gauge field. Anyway, the point is that this is a bit subtle to define because, but there's a way to define it if you think about this is about A is a Chern-Simons differential character, and then you can also define this as some natural Chern-Simons differential character. So there are different ways to define it without assuming that n is a boundary of anything. So anyway, so that's the answer, and in this case, the answer is very simple, and the possible anomalies are classified by a single integer. This k has to be an integer for this to make sense, because for this action, the action itself actually is not gauge invariant, but it's gauge invariant modulo integer multiple of 2 pi, and then when you exponentiate it, multiply by 2 pi I, multiply by I and exponentiate, then you get something well defined, which is a well defined weight in the path integral for A.
U1 theory, let's say this kind of generous Chern-Simons theory, but also not on 5-dimensional manifold. Nobody has any idea how to complete it.
Well, it's a classical one, right?
So I don't make quantum.
Yeah. Well, I can imagine there's some further terms in the action which can be relevant at long distances.
No, I can just consider A dA square, yeah?
Yeah, okay.
Form.
Yeah, but it's a classical theory.
I don't do Feynman integral.
Yeah, I'm going to do Feynman integral. But okay, so next, okay, what else can one say about? Well, nothing really. This is pretty much the whole story for this compact case, for a connected case. Now, turns out that in particular there are no anomalies in odd dimensions. Well, when d is odd, d plus 1 is even, so there are no Chern-Simons actions at all. So no possible candidate for anomaly. Indeed, there are no anomalies for U1 symmetries, or at least in free fermion theories. Now you can ask, what about, does it hold for arbitrary groups? For example, you can look at the sort of the opposite case when G is just a finite group. When it's finite, it turns out it's not true. First of all, the anomalies do not only arise from free fermion theories, so interactions do matter, and in fact, anomalies need not arise even from fermions. They can arise in purely bosonic theories. And second, they do not live only in they don't need to be restricted to even dimensional spacetimes. And moreover, even in the case when if you look at the case when the anomaly is, when the dimension is even, this d, that is, free fermions, can have anomalies. You can ask, okay, is the most general anomaly realized by free fermions? Turns out that no, the most general anomalies are not realized by free fermions. You need this extra new theories to realize some kind of anomalies. So, so let me describe this, how this works, what is the new mechanism which makes anomalies possible even in bosonic theories, and also how to classify anomalies. And then I'll also propose some generalizations of this which take into account some gravitational anomalies also, and some generalizations of symmetries. So, well, if I have time. Let me first propose an answer which classifies anomalies for, say, finite symmetry group G. So let G be a finite group. You got it right.
Weber will ask if it's not trivial.
Okay, Captain Obvious says that the group is not connected.
You say something else. Careful, get zero.
Thanks, Cap. Okay, so okay, I'm not going to make a general. Okay, so there's some further assumption I need to make here, because I cannot really classify all possible anomalies. I can say something about the most general case, but in general, it's not even true that the anomalies can be cancelled in this way. That is, here there's a topological filter in one dimension higher, with some action which depends on the gauge field, which cancels sort of the anomaly of the boundary theory. Now, it's not obvious, although it is true in the case when G is a compact connected Lie group, that it's not obvious that this can always be done. In fact, one can actually produce examples of the situation, well, station when G is finite group, but the anomaly, or 't Hooft anomaly, cannot be cancelled this way. That is, the obstruction to gauging is so severe, we cannot cancel by just adding some topological field theory in this d+1 dimensional bulk. But let me focus on the case when one can cancel using anomaly inflow. So suppose anomaly can be cancelled by this anomaly inflow from d+1 dimensional bulk, which means there is some topological field theory which does the job, and with this assumption, so anomalies are classified by topological gauge theory, well, by actions of topological gauge theories in d+1 dimensions. Now, okay, how can we describe all possible actions? Well, actually, it has been done by Dagraf and Witten a long time ago. So such actions are classified by maybe like 91. They're classified by d+1 dimensional cohomology of the classifying space of the group G, coefficients in U1 or R mod Z. I sometimes like to think of it as R mod. So, well, okay. First of all, so that's the answer that is stated.
Yeah. Okay.
But okay, okay. So our our space-times are assumed to be, well, usually assumed to be manifold, not just some
oriented. Yeah.
Oriented.
Yeah. Why? Yeah.
Well, in the real world, they're actually seen spin manifolds, but in general, we're interested in the case of a manifold which doesn't have to be oriented, or it may not have spin structures. So, okay, so let me just explain the answer. Then, indeed, one can propose. This seems to be a bit too rough. So the way they are reasoned is the following. Well, how do you write an action for topological gauge theory? Well, you have a gauge field A on some principal G bundle. G is finite, so it's the same actually specifying the G bundle itself. There's essentially unique connection. So you can think of A, if you wish, as just a way to define a bundle. So you can think of A as also as a map from your manifold M, which is well, here's d+1 dimensional because I'm looking at the d+1 dimensional theory, to the classifying space of the group. Well, and how do we make an action out of this map? Well, it's sort of like a sigma model. And if you want a topological action, well, presumably the action is an integral of some d+1 dimensional chain over the fundamental class of this d+1 dimensional manifold. Well, so well, you can imagine there's some there's some if you have cohomology class here, then you can just pull it back using the map and integrate. So, and the path integral, well, is a sum over such equivalent classes of such maps, or just maps, and each contribution of each such map is some element of U1, some phase. So, okay, so this chain should be valid.
Anomaly for each kind of principal bundle over MD, you should construct a torsor of U1.
I just want to, first I'm going to classify all topological filters in d+1 dimension.
For d+1, it means that it's for each.
So, so the Dagraf said, okay, let's just pick some class omega, some chain on BG. and write the action simply as an integral of the pullback of this guy, and provide the map to the classifying space, and that certainly is candidate action. And if that's if that's the form of the answer, you sort of, if you're, that's essentially the way to write a gauge invariant action. Well, I mean, this actually works even in the case when n is not a manifold, but just some CW complex. But in reality, okay, we're not interested in the general case. We're interested in the case when the space-time is a manifold. So as a result, it's really the correct, that sort of misses some actions which could have, because in principle, this action could depend not just, it doesn't have to be an integral of this sort. It could be it has some other dependence on the manifold n, except via its fundamental class, so, and the map A. So in general, one should probably use Cobordism of BG with U1 coefficients. So, and that has to do with taking into account essentially gravitation on, from the point of view of boundary theory. Well, so that actually is the correct answer to classify, oriented or unoriented, as the case might be. If you want to like field theory on, usually people consider oriented case. It should be a Cobordism. So, but I'll leave it now as it is. I'm just going to think about this situation. There is a map, by the way, from this group to this group, but it's neither surjective nor injective. So, surjective is not surprising. You could imagine that more general actions exist which depend on the gauge field and the manifold n in some more general way. For example, depend on characteristic classes of this manifold n itself. The fact that it's not injective is a bit more surprising. It means that there are some non-trivial cohomology classes of Digraph and Witten which actually lead to trivial actions, lead to trivial topological filter, in the sense that, if you integrate it over any, if you pick any manifold, in any G bundle on it, you will never get anything non-trivial, even though the class seems to be non-trivial. That's because the topology of manifold is just more restricted than topology of general CW complexes. Anyway, for now, let's just focus on this answer. Okay, so what does it predict as far as anomalies are concerned? Well, first of all, there's no reason for this group to be to vanish when D is odd. So we expect that anomalies exist in odd-dimensional spacetimes. And but I now can ask, okay, what sort of theory has a 't Hooft anomaly in odd-dimensional when D is odd? It's not free fermion theory for sure, because those don't have any anomalies in odd dimensions. Well, there is a mechanism. So there's a different mechanism for anomalies, as it turns out. So, and that's explained in detail in this paper. So, and the mechanism is this. So we have this. Suppose we have symmetry group G, and you can ask, okay, what is? Well, suppose also the symmetry we're going to gauge it, and but if you look at the theory itself, which is lives in the same this d-dimensional manifold, it can also have a gauge group of some sort, and let me call it maybe gamma. Now, and somehow, so that the complete symmetry group has this gamma as a subgroup, and the quotient of this total symmetry group by gamma is G, but what you get is not, just some short exact sequence of groups. G had need not be a product or even a semi-direct product. Typically, actually, it is. In most cases, it is a product or semi-direct product, but there are some more exotic cases where it's not. It's not, and then this possibility actually, it is this possibility which provides a new mechanism for anomaly, because you can imagine that well, let's look at a simple case when all the groups here are finite. It doesn't have to be the case, but suppose all of them are finite for simplicity. Then, well, we might have some gauge action for the gamma gauge field on the d-dimensional manifold M, which is described by some, say, Digraph-Witten action in d dimensions. Now, if you try to gauge it in d-dimensional, not going to d+1 dimensions, you would have to start with the cohomology class here. And try to, to extend it to g hat. That's the only way to gauge, g. But obviously, it's not always possible. There are obstructions to this. They have, we have embedding like this. But you just want to extend. If you want to extend the class from here to the big classifying space, you'll fail. So that's an obvious mechanism for anomaly. And I don't know how general it is, but one can easily produce examples of theories with anomalies in this way, which don't involve any fermions, and well, realize some interesting classes in this cohomology group. Maybe I should give you an example. So. So example. Well, actually, let me change notation so to conform with the paper. So so our g hat, the total, well, the symmetry group is G, and the gauge group is now called D. And I assume now, just to give a concrete example, I assume that D is just Z mod n. So it's a cyclic group. So so in this case, cohomology, well, and I also assume that D is 3. So it's a three-dimensional topological field theory. Well, in this case, one can easily describe so our 3D action of this topology, well, the theory on the theory on the boundary can itself be topological. It doesn't have to be. You can also add some matter fields, which will make it dynamical theory. But let's not worry about matter fields because the mechanism itself only depends on what the action for this D gauge field is. So, so H3 of B Z mod n with U1 coefficients is Z mod n. So possible actions are labeled by integer modulo n. So in actual, one can write a explicit formula for this action. So here, well, since the finite gauge theory, I'm convenient to use a triangulation. So we assume that our manifold M has been triangulated. And A is a simplicial Wanka chain on the manifold. Well, now triangulation is called K with values in Z mod n. Well, and imagine that we also actually maybe we lift it to integers. Okay. So so just Wanka chain, and it's some triangulation of M. Okay, so a three manifold, and well, I assume that the chain mod n And so that's the actual action, which is completely well defined. And the quantum theory is obtained by summing over all Wonka chains like that with this constraint. Okay.
2 pi I.
Yeah, so S, the way I normalize thing is that this action takes values in R mod Z. So the path integral, or in this case sum, statistical sum is sum over all A's of e to the 2 pi I S of A. So by the formula, it's like Chern-Simons theory, where instead of forms, I have simplicial cochains, and instead of D, I have delta. So by the way, even though here I assume that the gauge group D is finite, you can see that we can easily generalize to the case when D is say abelian, Lie group, so torus. Well, as for G, it's just going to be some arbitrary finite group. So I can ask, what does it mean to get? Okay, that's fine theory, but we're now trying to gauge the symmetry G. And what does it mean? Well, the fact that I assume that this extension is actually central for simplicity. It doesn't have to be, but just imagine it's central. Then we have some class of the extensions called C. What is the consequence when I try to gauge it? Well, when I gauge it, I have to introduce gauging G. Well, I need to do two things. So to introduce a Wonka chain A is actually going to be closed. But I need to do another thing. Like if the group were just a product, is G hat, then I wouldn't need to do anything else. But because it's not a product, I have to deform this constraint. And now again, I think about A as a map to classifying space of G. So capital A. So this is deformed sort of flatness constraint, and then and then I can also have to my action is now I can try to write the most general action, which reduces to the original one if you set this capital A to 0. And turns out in general I can't. While maintaining invariance under G hat gauge transformations. And one can actually just write the most general action and try to constrain the coefficients, and one finds that there's some obstructions. Actually, there are several obstructions, and it turns out in general, in this theory, not all anomalies can be cancelled by anomaly inflow, which I sort of assumed. That actually gives an example of the situation when anomaly inflow doesn't help in general. Just see. Okay, so well, so in this case, turns out that you need well, there are several obstructions, and the leading one is actually well to gauging, and so well, in this case, it's related to Z mod n. So now the leading one should vanish. Actually, is this one. So if you if you consider this, well, you can first of all try to lift these guys C to lift C to C tilde, which is some chain on BG with values in integers. Now that's not necessarily going to be closed, but it's differential is a well-defined, well, it's n times some cocycle, and the cohomology class of this cocycle gamma C in BG Z mod n is well defined, and that's actually the first obstruction. The first obstruction to gauging the symmetry turns out to be 2k times this class is 0. So this is the Bochstein. So this gamma is the Bochstein of C, and the constraint is this. So it depends on the value of k, which is the coefficient of net action, as well as, well, actually, when n is, in simplest case, when n is 2, so that actually vanishes identically because there's 2 here, but in general, you know, there's an real obstruction here. So, okay, so let's assume that that's the case, and then, well, if that's not satisfied, the anomaly cannot even be cancelled by anomaly inflow, but if it is, one can go ahead and check that if it's satisfied, then one can check that the action well, is invariant up to some fate, well, up to some shift by a 3K chain, which doesn't depend on this little a, but does depend on the capital A. And and then this cochain in general is non-trivial, and it's cohomology. Well, it's leads to an obstruction. So, so maybe in the simplest case, well, let me say n equals to, well, okay, fine. So, in case of n equals to 2, for simplicity where this leading obstruction always vanish, then the obstruction to gauging is C tilde, it's a Pontryagin square of this class C. So Pontryagin square is an operation which starts with the class in some in H2, say, of some doubly complex X with values in, say, Z mod 2. And gives you a class here. So it's sort of 1/2 of the cup product in some sense. Well, in this case, the abstraction turns out to be this this Pendragon square of this class C, and it can be cancelled by normal inflow if you take, the topological field theory to be this particular cohomology element. Okay. So that's a simple example of an anomaly in an odd-dimensional theory. It comes from the fact that there's a gauge symmetry in place, and the total symmetry group is just the extension of the global symmetry by this gauge symmetry. Now, instead of, well, in the paper we consider some other generalization, but let me look at the most interesting ones. So, well, one of them has to do with this extension from, the Graf-Witten classification of topological field theories, which takes into account that our space-time is not general C-doubly complex, but is a manifold. So one can then look at actions which are not just cohomology classes of BG, but cobordism classes of BG. So that's first generalization. So, anomalies from cobordism classes. And second generalization is anomalies for higher form symmetries. So let me first address the first one. Now, let's look at the extreme case. So, well, we can actually even take G to be trivial. So let G be trivial. Now, of course, in the case with cohomologies, it means that there's nothing interesting to consider. But if you look at cobordisms of a point, it's still interesting. Interesting abelian group. And what does it mean? Well, what does it classify? Well, if you believe this approach, then say omega, say SO of a point with U1 coefficients, which is by definition just this. It's the Pendragon dual of the Cobordism, d-dimensional Cobordism of a point to U1. So that supposedly classifies this topological field theories, which don't have any gauge field of their own, but they just nevertheless interesting topological field theories. Just the action depends only on the geometry of your d plus one dimensional manifold. And on the boundary, then you have must have something with a non-trivial anomaly. Anomaly for what? There's no symmetry here. G is trivial. Well, you can think of it as a gravitational anomaly. So this approach then allows you to compute, gravitational anomalies of d-dimensional field theories, which can be cancelled by this anomaly inflow. So that actually resolved some. Well, surprisingly, these anomalies have not been discovered before. Like in the 70s and 80s, when we look at those issues, but rather they were discovered recently by condensed matter theorists, because they noticed, well, in condensed matter theory, there is a notion of a symmetry-protected topological phase. So, namely, well, some phase of matter, which looks very boring in the bulk, but, well, there's some interesting physics going on the d-dimensional boundary. Interesting in the sense that, while if you put this, the point is that if you put this d plus one dimensional theory on any closed d plus one dimensional manifold, you also get, the partition function was just a a phase that is just an element of U1. And moreover, if you put this d plus one dimensional theory on any spatial slice of any topology, which has no boundary, the space of states is one-dimensional. So usually people think this as being a very trivial theory. However, doesn't mean that it's completely trivial, because the way the mapping class group acts on this one-dimensional space can be interesting. So in such cases, another way to detect something is interesting going on, that is not really trivial theory, is by looking at the boundary. If theory were really trivial, you could always have a trivial boundary. No interesting degrees of freedom on the boundary, but in the case of these protected phases on the boundary, you do find something interesting. For example, you can either have some actual physical modes propagating on the boundary, or you could have maybe interesting topological field theory on the boundary. That is, while this d plus one dimensional theory doesn't have any, well, its space of states is always one-dimensional if the manifold has no boundary. Well, if the d-dimensional spatial slice has no boundary, but if it does have a boundary, then you could have some degeneracy, you can have some non-trivial ground state degeneracy. So, okay, that was a long-standing sort of problem to understand how many such phases exist in any particular dimension. And, well, you can throw in symmetry in this problem. And people originally thought that the answer is given by the d plus one dimensional cohomology group of BG. But then they discovered that actually, no, there are some extra some constructions of these d plus one dimensional theories which give this interesting edge behavior in situations where this cohomology classification predicts something trivial. So the simplest example actually was the following. So let's imagine, let's see. The simplest example of the strange boundary behavior, which is possible but not described by a cohomology of BG, was the following: that you have a 3D, so suppose D is 3. And suppose you have the boundary, you have a Z mod 2 gauge theory. Okay. By itself, that's not terribly remarkable. Okay, it doesn't have to be a boundary of some four-dimensional manifold, for example, to exist. However, suppose you, for some reason, you want to force the following thing. So in this theory, there are two kinds of particles, if you wish, or which are represented by sort of loop observables in this 3D space. They may be knotted, I don't know. Okay. So there are two kinds of particles called electric and magnetic, and I don't know, call them E and M. And normally, well, you'll think, okay, is it possible to assign them some non-trivial statistics? So suppose I want both of them to be fermions. Is it possible? Well, ordinarily, in ordinary construction of this gauge theory on a lattice, both of these particles come out to be bosons. But suppose it's possible to have them both fermions. Well, it turns out there is no lattice construction which achieves that. Well, when the fact that they're fermions means that you need to, to define propagation of such particles, you need a spin structure on your boundary. Three-dimensional manifold also have a spin structure, but ordinarily don't need it to define this propagation of these guys. But it turns out that, so in 3 dimensions, strictly in 3 dimensions, there's no way to achieve that, but there are some 4-dimensional phases of matter where on the boundary have precisely this behavior. Both kinds of particles are fermions. And, well, how to explain it in terms of this classification? Well, you can notice that, say, omega 4, oh, wait. Actually, no, let me do the unoriented case, sorry. Okay. Suppose it's an oriented case. So in this case, so that's actually Z mod 2 plus Z mod 2. And the reason for this is that there are two different possible actions for this topological field theory, which depends on the topology of the manifold N. And the two actions are one was like this, and the other one is like this, where W1 and W2 are Stiefel-Whitney classes of the manifold N. So this kind of action doesn't depend on any extra gauge field, but depends on the natural cohomology class that you do have already, just by the fact that you're dealing with the manifold. So it turns out that, well, this action, say, corresponds to this situation when on the boundary have this kind of strange behavior. Z2 gauge theory where both kind of particles are fermions. That is, you can easily write down a lattice. Well, you can write down a lattice description of this theory such that on the boundary have this behavior. So that's one possible application of this. So it sort of this classification of anomalies also predicts some interesting phases of matter in one dimension higher. So, and another generalization one can make is so suppose well is this higher form symmetry. Let me put this. Well, what is a higher form symmetry? So higher form global symmetry. Oh. So, well, so what is this? Well, it's a symmetry whose parameter depends on a closed Q chain with values in some group. Well, in this case, it has to be abelian if Q is greater than 0. And what does it mean to gauge this symmetry? Well, so gauging, same as dropping the close condition. And also adding some gauge field, which is a Q+1 cochain. Now, typical example is like this. So example of this. Well, it's often the case that you have some. Well, suppose you have some. Let's for concreteness. Suppose A, so let A be an ordinary gauge field. For some G. G is, like, say, compact. Well, not G, called D again. In this case, let me just take to say it's a compact. Well, like, let me be even more concrete for SUN. Typical favorite example in physics. Now, and suppose all the matter that you have in this theory is not charged on the center of SUN. Then the symmetry. Well, like this. So you can sort of shift your gauge field by a flat gauge field with values in the center of the group. So that's a symmetry because the action itself actually doesn't change at all. The action of the gauge system, and also the action, the coupling to matter field doesn't care because they're not charged under the center. Well, so this is an example of a one-form symmetry. You can ask, can you gauge it to promote this to well, this alpha, which is here is a closed one-cut chain, to just an arbitrary one-cut chain. And again, that maybe abstraction to doing that. And so what are they, you can ask what are they classified by? And again, if you assume that it can be cancelled by anomaly inflow from one dimension higher, then you can classify all, well, in that case, the analog of this Dagger-Witten theory is some theory in one dimension higher, which has a sort of a gauge field, but this gauge field, well, in the usual Dagger-Witten case, when it had dealt with an ordinary symmetry, the gauge field was an ordinary gauge field for the symmetry group G. But here, the parameter itself is a Q chain, so the gauge field is going to be Q+1 chain. So in this case, one needs to deal with sort of Dagger-Witten type theories where the gauge field is a Q+1 chain in one dimension higher. So certainly that works, and well, the answer in this, for the kind of actions we need is the following: that in this case, I'm assuming that my symmetry group G is abelian. Well, not this one, but the one where the chain takes value, like say here it's Z mod n. And the actions are classified by, well, either by D plus one dimensional homology, or maybe cobordism of the iterated classifying space. You can look at if a group G is abelian, you can actually iterate the construction of the classifying space, and you sort of have like a Q plus one fold classifying space of G, and cohomology groups of the space classify possible actions for the such gauge theories and topological gauge theories, and therefore classify also anomalies for symmetries in one dimension lower. Okay, so actually there are examples where this anomaly is non-trivial. So having to do with, say in 4 dimensions, there are examples. Sorry, in 3 dimensions again. If these 3, there are examples where this cohomology group is non-trivial, and there are actually very simple examples of field theories, which are also realize as anomaly classes. I'll stop here.
Alright, let's thank the speaker again, and we'll proceed at 10:15.